Okay, chemical kinetics. Here we are talking about the reaction rates and reaction mechanisms. I was just talking about the Arham, and he became this top student of chemistry of Sivali school, and then Anuradha, the Arham from maths, Arham from English medium. That is the thingy. Like they say, English medium students of these government schools are weak. They are not weak. They maybe they get weak if you're not studying enough. Even Nadisha, she came only to me so far. She became top 10 of Ferguson. So those are like plus good points. So just stick to the plan so that we can do this nicely. So we are going with these chemical kinetics, instantaneous reactions, moderate reactions, and slow reactions. That easy, can just understand very easily. And this is even we did at the very beginning. This is you can use continuously all the time. If you want to calculate the rate, that is the concentration difference divided by time difference, or pressure difference divided by the time difference. So the units always moles per cubic decimeter per second or Pascal per second. And with respect to product's rate increases with time because the concentration increasing. Reactant rate decreases with time because concentration is decreasing. Then we just touch these experimental techniques, and then I've given you guys a couple of these factors affecting rate and how you're going to illustrate that at the exam if they ask you guys questions. So then the first calculation part starts from here. Mathematical expressions for rate with stoichiometry. And rate, see, we already calculated, we already got to know how to find the rate. Rate equals concentration gradient divided by the time difference. But if you have different stoichiometries, if we need to equalize these rates, what we're supposed to do is to get per mole rate, we have to divide each by their own stoichiometry. At the same time, since reactants are disappearing with time, reactant concentration is decreasing, we are adding negative sign here. So once we do the calculation, negative multiply this negative become, cancelling off become positive. So at the very first question, did you do this at the class? Both? Yeah, first one. Second one, can you check? So H2 and I2 are reactants. So values are negative, but the stoichiometry is 1. So that 1 divided by 1, come darling, 1 divided by 1. And then this is a stoichiometry equals to 2. So this is become 1 divided by 2. Central is missing. All the others are missing anyway. I've started because, you know, I don't want to waste her time. We did that last little part of organic conversions. I would send this recording, okay? And here we are starting. And this is again homework. Okay, so color question number 2, chemical kinetics. See, so this is a nitrogen peroxide and this is a reaction, and they are saying rate of the reaction with respect to formation of NO2. Rate is this. Okay, if we write the total rate expression with respect to stoichiometry, so N2O4 you have 2, NO2 4, and O2 1. So you can divide by 2 and 4, and this is just a 1 here. And since this is reactant, I'm going to add negative sign here. Okay, so this is a full expression. This is a full expression, but then they were given this rate, not with this 2. They are just giving, sorry, not with this 4. They are just giving rate with respect to NO2. So rate with respect to NO2 is this one. So they are giving that value equals here this. Understood? This is the connection, Karan. This is the connection. Knowing that whatever they ask, even if this or this, we can now just need to substitute. See, now this is the expression that I know the data. dNO2 over dt equals this value. So the connection between NO2 and O2. NO2 and O2 is, we already written, is this. Then we know this part. So I'm going to substitute rate value for this part here. But to get this oxygen rate, we have to divide this part by 4 so that the answer becomes 2.1 into 10 power minus 6. Same way with respect to N2O5. So this is the connection now. Half N2O5, 1 over 4 NO2C. This equals to this. These two are equal. Okay, so that I'm going to write the exactly same expression. See the same expression I'm writing here. I can cancel off this 2 to this 2 here. Just I'm going to keep the negative sign. Okay, I'm going to keep the negative sign just to show it is reactant. Then if I simplify this one, divide this by 2 because this is 2, then the answer is 4.2 to 10 to the power minus 6. Could you get these answers? Okay, copy from here if you haven't got the answers. Got it. Good. And this part. Yes. Okay, so before the third question, let's write this little point. In calculations, about the third question, let's write after the second one. In calculations, the rate of consumption of reactant is multiplied by minus 1. Multiplied by minus 1. Okay, so the next question, again you have this ABCD normal equation. So just a normal equation with respect to stoichiometries are A, B, C, and D. At a certain time, rate of formation of C is this one. Rate of formation of C equals to R. So we can write the normal rate expression this way, as we did for theory. Then again, they say rate of formation of C, this part, equals to what? This is equal to R. So that is our connection. So they're asking rate of disappearance of A. So I'm going to go with these two. This part, I'm going to equalize to this part. So that I can just write this. 1 over minus 1 over A into dA over dt equals 1 over C into dC over dt. And then they say dC over dt equals to R. This little part equals to R. So that for this dC over dt, now I'm writing R. Now you can subject this part. Just subject dA over dt, the negative sign here. Then you're going to bring the A out other side. Then it equals RA divided by C. Good, well done. Okay, so then the second one, rate of disappearance of B. So that I'm going to go with the B part. And this is the B, which is supposed to be equals to this. So I can rewrite it here. Then again, same way, dC at dt. dC at dt, this equals to R. Then when I'm subjecting dB over dt, negative, then this B comes to the other side. Then this B become multiplicity RB over C. Same way. This again equals to R. So that is, if I subject this part, the dd over dt, that's become RD over C. Clear? Both good answers. Good. Okay. That's all we did. Okay. Today is the day that you are really understanding the principles of chemical kinetics. Okay. For the rate law is the part that is the base or the principle of chemical kinetics. Once, so we're going to do the rate law for this first zeroth order, first order, second order, third order, so on. So when you are starting the zeroth order, you would feel it's a little complicated, but zeroth order to first order, second order, third order, all are exactly same. Then once you go on one by one, then you understand this better, okay? So just hang in until you go on a little longer. Otherwise, you would feel a little frustrating. This is little unclear or something, but this is not unclear something. Very little comes to the exam, okay? So let's try the topic. Rate low, rate low, rate low. Okay, this is the rate law. Rate of any component is proportional to some sort of a power of reactance and then the multiplicity of reactants. Okay, so let's say we have only one single. Let's say we have A goes to B. Then what happens is rate equals to concentration of S, some sort of unknown power. To this power, they are given a name which is called the order. Then let's say we have A and B, two different reactants. Then we are raising them to some sort of a power. This power may be equal to stoichiometry, maybe not equal to stoichiometry. Let's consider that later. Anyway, some sort of a power. And this power is called the order. So we can name M as the order with respect to A. N mean the order with respect to B. See, M, order with respect to A, N, order with respect to B. To remove the proportionate sign, we can add a constant. Here we are talking about the rate, so that this constant is called the rate constant. To remove the proportionate sign, so that we are adding rate constant. Clear that? Okay, so okay, let's say we are going with the concentration. So what is the units of rate? Delta, concentration divided by delta T, that is moles per cubic decimeter. Let's say time is per second. We did that earlier, remember? Okay, these are the units of rate. Rate equals concentration difference divided by the time, moles per cubic decimeter per second. So moles per cubic decimeter per second. No? Just WhatsApp me. Maybe she has WhatsApp, I didn't check. That's how she needs it. Oh, they are requested. Just usually, I didn't hear their messages. Like Sanujana and Tashi both requested links. Anyway, so this is the unit of rate. Okay, this is the unit of rate. So I'm going to go back to that equation then. Then unit of rate is already fixed. Let me know if they request here. Then unit of rate is constant. It's not changing. Unit of rate is the rate with respect to concentration and time. And concentration units are also not changing. See, this is the rate unit. It's not changing. Concentrations are not changing. If anything's supposed to change, that's supposed to be the units of K. Clear? To get K's units, what do we need? We need these units and these units. But what we have now is not just the normal units, we have the powers. Oh, wait a minute. So we have powers. So that then we have to get to know what is this m and n to get units of this k. Is that clear? Okay. I have to break to explain this. So anyway, then again, if we go more about with these orders can be 0 to any of these 1, 2, 3, 4 integers. It can be also negative. It can be also fractions as well. And rate depends on temperature, and also rate constant also depend on the temperature as well. And it depends only on the temperature, same as the equilibrium constant. Equilibrium constant and rate constant depends only on the temperature. Okay. So let's write all those little information. And then let's go to talk about one by one of these different orders. So the topic is rate law. Let's write points. Rate of a chemical reaction. Rate of a chemical reaction is directly proportional. Rate of a chemical reaction is directly proportional to a certain power of concentration of reactants, if the other factors remain constant. If the other factors remain constant. Okay, let's copy only this part. Okay, M, order with respect to A, N, order with respect to B, K, rate constant. K, rate constant. Just hang in until we do a couple of these orders. After that, if you feel uncomfortable, then let's discuss questions. Okay, so let's write normal points. Units of rate constant. Thank you, darling. I was waiting until these others are coming online. Are you understanding this part? You just started, okay? Units of rate constant K. Units of rate constant K, comma, depends on order of each reactant. Order of each reactant. Tashmi, we just started from this rate law, okay? We started from rate law. Units of rate constant K depends on the order of each reactant. Within brackets, M and N. M and N. Without the first part, this is a little harder to understand. Next point, M and N can be, get a screenshot, I'm going to scroll up. M and N can be 0, 1, 2, and 3, so on. 0, 1, 2, 3, just dotted line. Next point, for a given reaction, for a given reaction, comma, rate constant is characteristic. Rate constant is characteristic and K depends only on temperature. K depends only on temperature. K depends only on temperature. Next point. There are few examples of fractional orders and negative values. Fractional orders and negative values. Fractional orders and negative values. Next point. Order of a reaction. Order of a reaction may or may not be equal. May or may not be equal. May or may not be equal to stoichiometric coefficients. To stoichiometric coefficients. Stoichiometric coefficients. Next point. In complex, within bracket, or multi-step reactions. Okay, let me explain that little part. Okay, let's say A goes to B. So directly there is no any other something. You have one single intermediate. Through that intermediate, you are just converting A to B. But let's say there is another reaction. A goes to C, C goes to D, and D goes to B. Two different kinds of reactions. Directly A goes to B, that kind of reactions are called single step or elementary reactions. Single step or elementary. If reaction goes through a couple of reactions, couple of steps, that is called complex or multi-step reactions. To these we are coming later. These are like the later topics of this unit, but I'm making all this little summarization under this order part. Come on, Karan. Okay, so multi-step means there are a couple of steps in the mechanism. So let's write in complex or multi-step reactions, comma, order can be or cannot be. Order can be or cannot be equal to stoichiometric coefficients. Order can be or cannot be equal to stoichiometric coefficients. Stoichiometric coefficients. Okay, next point. But in an elementary reaction, or within bracket, single step reaction. Elementary reaction or within bracket, single step reaction. Single step reaction. Angela, make it in here. Rice and curries in very hard gravy out there. But in an elementary reaction or single step reaction, comma, order with respect to any of reactant. Order with respect to any of reactant, comma, is equal to stoichiometric coefficients is equal to stoichiometric coefficients of the balanced chemical equation. Of the balanced chemical equation. Okay, this is just a summarization. Balanced chemical equation. Okay, if it is a complex reaction, order can be or cannot be equal to stoichiometric ratios. But if it is a one single reaction or elementary reaction, order is definitely equal to stoichiometric coefficients. We're going to come to that later. Here I'm adding all the points that are necessary for talking about the order. And the other thing is, if you want to calculate this or to determine this stoichiometric coefficients, how do you do that? How would you do that? Stoichiometric coefficients are the balance stoichiometric coefficients of a reaction. Let's say we are writing like sodium plus HCl, sodium chloride plus H2. Then whatever you are adding here, those are the stoichiometric coefficients. By balancing equation, you can get stoichiometric coefficients. But to get order, definitely you have to go with an experiment. Order, it's a must to go with experiment. Stoichiometric coefficients, just writing the balancing equation, you can get that. Let's write that last point. Order of any reaction, order of any reaction should be determined. Order of any reaction should be determined by an experiment. By an experiment. Order of any reaction should be determined by an experiment. Okay, so here we talk a little extra about orders. So we're going to go with one by one, 0, first, second, third orders. So 0 order means there is no order. Like if we write this expression as, let's say, here we are writing 0 here. That is called the 0 order. If you write 1 here, that is the first order. Let's say we write 2 here. So with respect to B, this is a second order. So this is the order part. Let's say that we have 0 here. That is the 0th order. What's the meaning of 0th order of any something? Equals to what? Let's say 2 to the power 0 equals to what? 1. 6 to the power 0? 1. Or A concentration to the power 0? 1. It's exactly 1. What's the meaning of that? 0th order mean, if this is 1 mean, there is no effect from this concentration to the rate. Understood? 0th order mean, there is no effect. That is the base. So let's try the topic, 0th order reaction. 0th order reaction. Okay. So if it is 0 order, reaction rate cannot change by this reactor. Let's say we have A and B gives C. Then we are writing the rate equals A to the power 0 and B to the power, let's say something 2. Then A to the power 0 mean what? This equals to 1. So we are writing the rate as so that A rate equals K B to the power. A is not here. K B to the power 2. So A is not here. Does it mean, let's say A and B together give C. Does it mean we don't want A? We need A. Because B is supposed to react with A to give C. What is the difference? Here we are not talking about how much product is making. Here we are talking about what is the rate of formation of product. To understand the rate, we don't want A. Clear? What is the reason for that? A is supposed to join into faster reaction. Okay, remember that we did organic chemistry. I said that, let's say Nidula and Nidula small Malli, I guess. We got the example. Okay, then let's say you have a little sister, like, the 5-year-old sister. And this is you, tall, strong, and faster. So you both are going somewhere. You cannot carry her. You have to walk. Then who decides the speed? You would say that. But she is deciding the speed. You have to go to her speed. Ane Parakuna, she was slow because she was walking very slowly. Let's say that you are going somewhere with your grandma. Then they are slow. Then you have to go with them to their speed. To Nangi, you can even yell. To your grandma, you can't yell. You have to hear that, okay? So they are the people who deciding the speed. So those are the species who deciding the reaction rate. Then who is A and who is B? Let's say this is 1, this is 2. Which one is A? Let's say A to the power 0, B to the power 2. Who is A? This is A, because we are not counting this. Understood? Doesn't matter how speedily you can react. Who's deciding the reaction rate? B. Whatever the B's power, that's deciding the rate. Is that clear? So A is the one which we call the zeroth order because it cannot control the reaction rate. Clear that? Okay. So let's write points. The rate of zeroth order reaction is independent of reactant concentrations. Reactant concentrations. Next point, when a reaction is in zeroth order, comma, all the reactants are involved in fast steps. All the reactants are involved in fast steps of the reaction mechanism. Within bracket, slowest step is the rate determining step. Slowest step is the rate determining step. Okay, there are a couple of examples. H2 and Cl2 gives HCl. Ammonia ammonia breaks down in the presence of tungsten or molybdenum to nitrogen and hydrogen. N2O breakdowns to give N2 and O2. And this is the reaction between this ketone and this I2. But we didn't do this reaction for organic chemistry, okay? These are zero order reactions. So let's write those. Copy those. Hello? Oh, කාටද දන්නේ නැහැ කියන්නකො කාටද කියලා පන්ති ඕනි 2026 සිංහලද ඉංග්‍රීසිද ඔව් එයාට ඕනි සිංහලෙන්ද කරන්න යා ඉංග්‍රීසියෙන්ද කරන්න දුව ඉන්නවද හා කතා කරන්නකො No, දුවට ඕනි 2026 සිංහල මීඩියම් කෙමිස්ට්‍රි ක්ලාස් එකද? ඒ ක්ලාස් එක තියෙන්නේ සිකුරාදා හවස 2:30 6:05. ඔව් මේ සතිය අලුත් පාඩම පටන් ගන්නවා. මේ සතියේ එන්න යාළුවන්ටත් පණිවිඩ තියන්න අලුතෙන්ම පටන් ගන්නවා පාඩම. තියෙන්නේ මේ අර මොරගහට පාලම ළඟ. දුවේ කොහෙද ස්කූල් එක? දැන් යන්නේ කොහෙද? ආහා හරි පර්මනන්ට් පැත්තෙන් එන්න කට්ටියක් හිටියා. එන්නකො මෙතනට කට්ටිය ගොඩක් එනවා පෙනේ විවාට. හවස 2:30 මට WhatsApp message එකක් දාන්න මොනවා හරි තව විස්තර ඕන නම්. මොරගහට පාලම පහුනහම එතනම තියෙනවා. හෙට තියෙනවා. ඔව්. හරි. Okay, so now we're going to start the real chemical kinetics from here. So this is here we're going to go with these rate expressions and also some graphs as well. Let's say here with respect to A, this is 0th order. When we are writing rate expressions with respect to stoichiometry, how do we do that? Like we can write minus 1 over A, dA concentration at a dt equals 1 over C, dC concentration over dt. So when you are writing rate expressions for with respect of stoichiometry, we can go with either reactants or products. Clear? But when we are writing rate expression using the rate laws, we are writing rate expressions only for reactants. Clear? Only for reactants. So if you go with this one, we have only one single reactant and its stoichiometry is A. So let's say with respect to A, it's 0th order. Okay, we can write the commonly rate equals, commonly we can write rate is proportional to A's concentration, some sort of a power. So X is the order. And let's consider that order equals to 0. Okay. Then if I need to remove this proportionate sign, I'm adding the proportionate symbol, that is the rate constant actually. I'm going to go with K prime here because I'm going to add K later. Okay, so I can, instead of this one, so I can write this one. Is it clear from here to here? Then X equals to 0 because it's 0 order. When 0 order reaction, X equals to 0. So that I'm writing instead of that, it's X, I'm writing R equals K prime a to the power 0. Anyway, a to the power 0 equals to 1, so that I can come to my first equation, R equals K prime. So my very first equation is R equals to K prime. I'm making it as equation number 1. Then, at the same time, see, remember earlier I said case units depending on A and it's these orders. Since here K equals to R, what is the R units? R units, concentration divided by time. So R unit is mole per cubic decimeter per second, which become the units of K. Okay, another knowledge of that. Then if my first equation is R equals K prime, my second equation, if I go with the initial rate equals initial concentration divided by the time. Initial concentration, let's say I'm using 0.5 mHCl, then I know the concentration. I can always use the same initial concentration so that I can make it constant. So then let's consider this initial concentration. Initial concentration is constant, and I'm going to get that constant as K2. So that here R equals, instead of this A, since it is constant, I'm going to write, instead of A, I'm writing here K2. So that instead of this one, I can write R equals K2 over time. And then concentrate well. Here I have R equals K prime. Here I have R equals K2 over time. So what I can say? I can say so that K prime equals K2 over time. K prime equals K2 over time. So that K prime equals K2 over time. So K prime, K2 both are constant. I'm going to divide 1 by 1, cross multiplying. Time goes here, K prime goes here, K2, K prime cancel off, become K. T equals to K. And Shamodi, I guess you've done this at school. So what is the meaning of T equals K? Kalna, what is the meaning? Time is constant. Which time is constant? With respect to A. Even if we change concentration of A, time taken to do the reaction is exactly constant, not changing. Why? Because that is a faster reaction. Who decides the reaction rate? The slow one, your little sister. So she decides. You are not deciding. So regardless, what are you playing? What are you doing? It doesn't change the time. Is that clear? Understood? So with respect to you, it's constant because you are independent of your rate. Whatever the faster rate is independent. Clear? So that even if you change or even if you not change, the time taken to that with respect to that is constant. So that we can write this way because even when we change the concentration of A, if we measure the rate, different rates, what happened to the rate? Rate is not changing. Even if you change this one, because it is zero order. Clear that? So, since R equals to K, even if you change A's concentration, rate is not changing. Okay, then this one. So, I'm going to go with concentration A and time T. Okay, what happened to the concentration of A when the time is passing? Okay, A plus B gives C. With time, what's happening? A is using, B is using. Both are using. A is using. So with time, concentration of A is decreasing. But that decreasement is again constant because with respect to A, it's zeroth order. See how you can understand that. Okay, so the rate equals concentration gradient dA divided by time difference. So I'm going to get a piece of A. Okay, let's say this is a piece of A. So this is like, you know, the Y2 parts. Y2 minus Y1 or whatsoever. If I get with 2 points, let's say this is the initial and this is the final. And if we get this, so this is the concentration difference. And if you go here, this is the time difference. So that the concentration difference divided by time difference supposed to equal to what? Supposed to be constant because with respect to A, rate is constant. Understood? So that when we are drawing this graph, gradient supposed to be constant. Then only we can say rate is constant with respect to that reactor. So that you are getting a straight line which has the negative gradient. Come, darling. Papa, kala enawada? Kayawada? Your lunch. Are you okay? So at the break, you can have them. Come on, what are you guys doing? Unbelievably. What are you guys doing? You guys are like so addicted, everybody, to this science day. Huh? So they are not that addicted to studies. But to science days, they are like unbelievable. Yeah. And yeah. Oh, they mean who? Your friends. Oh, the rehearsal. To do the drama tomorrow. And they will start after. But oh, yeah. They didn't start at 1:30. They started at. The thing is, Putra, it's really obvious each year this is happening starting from 2019. If you are so much into those stuff, if you forget, like, if you, like, you know, this half day now we are using for something other, then you don't have in another time to watch the recording. If you gather a couple of recordings, you cannot do this. I don't know why these teachers are doing that. But they would always praise students who has the exam. Never forget that. Okay, Nidula, you may not understand this properly. I will come to you and explain this little later. Okay, then listen others. Then again, rate is constant. Rate is constant. So if you go with rate and time, even when the time is passing, when we are changing the concentration of A, see, rate is not changing. So these are the 3 graphs that you are explaining using zeroth order reactions. Is this clear? Okay, Nidula, I'll come to you. Just hang in. Okay, let's write this point. Hang on. Did you write up to here? We were here. Okay. Copy this down. Copy everything. Copy everything. Let me talk to Nidula for a second. Then 0 order. So we know on this here. We got the period expression rate close to that. So yeah. So then rate is proportional to concentration to the power. But x equals to what? Your probability 0. So x equals to 0. Any power of 0 power of any equals to 1. 1. So this is 1. So r equals to the power 1 in r equals to 3. Then again initial rate. Initial rate equals concentration divided by time. But we can make initial rate constant. So instead of I'm writing A, initial concentration is constant. It's the last rate so that rate equals equals what? It equals like this one. This A is related to fastest. I told you I use this to going somewhere and so this is U. You are not deciding the rate. The efficient U concentration is constant. See, now A is changing, but rate is constant. This one I understand. A concentration, A or B concentration. That's basic, but it has to be constant to make it independent from S. So then it's supposed to be a straight line with rate with time is constant. If possible, copy, otherwise you can do this. Or otherwise leave the page, you can do this by getting the recording. Shamadidal, how is chemical kinetics for you? Okay. Did you guys start equilibrium? Really? How is that? For now, okay. Now it's getting complicated. Chemical equilibrium. Now equilibrium is extremely easy to just hang in. I'm going to finish this soon and go there. Okay, Nidula, I'm not going to give you time, okay? I'm going to move. Leave the space. Kalna finish? Okay, leave the space, Nidula. Look at Kalna's one. This much you have to leave, okay? Start copying here. T equals K. T equals K. Then let's write this point. Therefore, the rate of zero order reaction, therefore, the rate of zeroth order reaction does not vary with reactant concentration. Does not vary with reactant concentration. Therefore, R equals K. Therefore, R equals K. Okay, now draw these three graphs. For my students, equilibrium is always easier That's again, I would say, you guys have to participate every day. Equilibrium is really challenging. Angela? පොඩ්ඩක් ඊටත් වැඩිය හොට් දෙන්න. ටික විසි කරන්න. Moving on. Okay, then how do we know any reaction is zero order? Any reactant is zero order. We change the concentration, but still the rate is constant. Rate is not changing. So then we can decide it's zero order with respect to that reactant. Because even if we change the concentration, see the rate is not changing. Rate is constant. Rate is constant. Let's write that. Therefore, even if we change, even if we change the reactant concentration, comma, if reaction rate does not change, comma, that is a zero order reaction. Zero or zeroth, both same, okay? That is a zero order reaction or zeroth order reaction. That is a zero order reaction. That's all with that. So let's move on to the next topic. First order reaction. First order reaction. First order reaction. Okay. Couple of examples are there, but they never ask whether this reaction is first order or not. But in your syllabus, you have a couple of examples. See, with respect to this is esterification. Sorry, ester hydrolysis. With respect to the ester, it's first order. And with respect to this sucrose, it's first order. And here again, with respect to this reactant, it's first order. Okay, let's copy all this. Thank you, Papa. I know you're faster, that's why I didn't care. Copy this. Anybody wants hot water? I had it. Really? Oh, no. Where does he live? Palmadulla. Havatta? Oh. Tony, where are you living? You are coming from Palmadulla. I thought Shamodi, you are living close by. support me to go faster with covering the syllabus so we can start questions, continuous questions. That is the secret of my successness. I'm really glad like when these students are showing me like this higher successness. So we have promising results for 2024 this time. Maybe the district first, who knows? Let's see. And Nidula, you know, Arnam had the highest for chemistry this time. Out of school. Yeah, amazing. I'm so glad with that. English medium, see? Keep it up. Amazing thing is he wasn't always the first person. He was falling back, then I'm pushing him back. They're going like that. Okay. 2 more is there to write, 3 more. Just copy these 3. All these 3 are again 0 order. See, I told you guys these reactions are very relevant in inorganic chemistry. All right. See, the same way we are going with the equations. So this time it's first order. So I'm writing again, this is my reactant. So rate law goes with reactants. So I can write rate is proportional to A's some sort of a power. So Y is the power. To be first order, Y is supposed to be equal to 1. So Y is supposed to be equal to 1. So that rate expression I can write 1 to the A to the power 1. So R equals, to remove the proportionate sign, I'm adding proportionate symbol. So that I can write R equals K A to the power 1. Is this clear? Okay, then I'm just skip this part. Then I'm just coming from here to here. The same way I can say, if I go with the initial concentration, I can write again, concentration divided by time is a rate, but initial concentration I can control to constant. Let's say that constant equals to K2. So from this equation, I can write, instead of this A, I can write K2. So I can write rate equals K2 over time. Here, remember, rate equals K prime A to the power 1. Rate equals K2 over time. Rate cancelling off. So that I can write K prime A to the power 1 equals K2 over time. K prime A to the power 1 equals K2 over time. From that, if I subject A, this K prime goes to the other side. Then K2 divided by K prime is supposed to be equal K. So that 1 over T, I'm just writing here. So that A equals K into 1 over T. Are you guys okay up to here? Yeah, last time, what is that? Yeah, k equals t. Last time just k equals t. Why? A is not there because a to the power 0 equals to 1. So concentration doesn't matter last time. This time we need the concentration. Which power? To the power 1. Okay. So if I go with these graphs now, we have two equations. My first equation is R equals Ka to the power 1. Okay. R equals Ka to the power 1. R equals Ka, which is Y equals Mx kind of a graph because we know K is a constant. So if you write Y-axis as R, Y-axis is R, and let's say our X-axis is concentration of A. So you're supposed to get Y equals Mx kind of a graph, which is a straight line going through the origin. Clear? Okay, so this is the connection between R and A for what? For first order reaction. First order reaction. And see, the second connection. A equals K into 1 over T. If I go back with that, if I remove the constant, I can go with this proportionate sign so that I can directly say A is inversely proportional to time. So when concentration increases, less timing. Concentration decreases, more timing. So we know concentration increasing, then time rate is high. Rate is high mean time taken is less. That's why time is less when concentration is high. Clear? Okay, see. For that, I'm giving you guys this little explanation. Let's say A is proportional to 1 over T. So 20 is proportional to 1 over half. Then when I decrease this is supposed to be also increasing. See, when A is 20, T is 2. But when I increase concentration, so 1 over T is supposed to be decreasing. So this is here it's 0.5, here it's 0.25. Clear that. Anyway, from here, if you calculate K value, it is same. It is not changing. K is constant. Understood? So one is increasing and one is decreasing. If you draw a graph to that, okay, at let's say the concentration high, time is lower. Then concentration lower, time is high. So that you are ending up with this kind of a graph, which is called the hyperbolic curve. If you go with 2 points, if you understand that, I'm going with X and I'm going with Y. In X, see the concentration is high, but the time is small. And if you go with Y, see the concentration is small, but the time is large. Understood? So that you are getting this kind of a graph for first order reaction. If you go between A and T, because these two are inversely proportional to each other. Now tell me what is the graph if you go with A and 1 over T. See, A and 1 over T. Y equals mx. What is the x-axis? 1 over T. Y-axis, A. See, between A and 1 over T, that's a straight line going through the origin. Understood? Okay, see again. Now we are going with this first order reaction. So we are writing same way. Let's say we have one reactant A. So with respect to A, its order is Y. So that rate is proportional to A to the power Y. But let's say that Y equals to first order or Y equals to 1. So A to the power 1. So my first expression is R equals K A. Then my second expression for initial concentration rate equals initial concentration divided by time, but initial concentration is constant, so that we can write R equals K2 into time. Then R and R equals, so I'm going to make K prime A equals K2 over time. K prime A equals K2 over time. So get the A to A here, subject. Then I'm going to make this K2 here, K2, K2, K prime. K2 divided by K prime k2 divided by k prime is just another constant. And I'm leaving this k1 over t here. Then if you go with graph, for the first expression, r equals ka, y equals mx. If you draw the curve between r and a, that is a straight line going through the origin. And this has inverse relationship. A is inversely proportional to t. So if you draw with a and t, whenever t is high, a is low, inverse. Whenever t is low, a is high. So that you're going to get this kind of a graph. But if you go with just the real a equals k into 1 over t, if this is 1 over t, reciprocal part is we already added to 1 over t. Then y equals mx. A is y-axis, 1 over t is x-axis. Then again, you're going to get this y equals mx kind of a graph. Understood? All right, let's copy. Yeah, from the beginning. I guess, hang on. See, I just keep this part here. At the same time, I'm giving you guys the units of k. K equals what? K equals r divided by a. Then what is the units of r? Moles per cubic decimeter per second is the units of r. And then the a concentration. So units of a is moles per cubic decimeter. So moles to mole per cubic decimeter cancelling off. So for the units of rate constant of first order reaction. First order rate constant unit they are asking these for exam just is per second. They are just asking for MCQs, what is the order for second order reaction. Then you have to, if you memorize, it's easier. Otherwise, you have to find that. Okay, let's copy this. Kinetics is easier, not like equilibrium. Kinetics is easier and simple. Equilibrium is easy, but it's really complicated. Because you even don't remember the first part when you're doing the last part. Sort of same as organic chemistry. Because it's that long, equilibrium. That's what I'm worrying, having these 10 months. Because before COVID, I've covered the full syllabus ahead of 10 months of the time. But still we are doing unit level. But I'm really happy with our condition comparing to other students' condition. Can I go up here? Yes or no? Okay, draw this. Draw these three graphs. Okay. If you have any question now, you can discuss it. Maybe because the second order and third order, we are going exactly the same way. We understood this. Going on to the second order and third order is easy. Any question? Understood. I know for now it's very blur. It's not 100% clear, but I guess you understand what I'm saying, the facts I'm saying. So when we are doing, until we do questions, you are not understanding this nicely. And here again, see, when you are increasing concentration, rate is increasing just by twofold. So because rate is proportional to concentration, so if you make the concentration twice, the rate is also become twofold. If the rate is become twice, when you increase the concentration twice, then what is the order? When you change the concentration twice, if the rate is double, then what is the order? First. This is first order. Neither. If you change, listen, neither listen. If you change the concentration, if still rate does not change, that is 0. If we double the concentration, rate also doubles. First order, because it's proportional, just the directly proportional. Understood? Okay, so let's write that. Since R is proportional to concentration of A, since R is proportional to concentration of A, comma, twice the reactant concentration, comma, doubles the rate of the reaction, comma, in first order reaction. Okay, so that is right. Therefore, when we, next point, therefore, when we doubles the reactant concentration, comma, if reaction rate doubles, the reaction is first order. The reaction is first order. If reaction rate doubles, the reaction is first order. Okay, let's try the topic. Second order reaction. Then let's copy all these for examples. Example 1, decomposition of ozone. Copy these for examples. Example 2, example 3, and example 4. Finish. Okay, here explanation is even easier for me. See, now same way, let's say A goes to B. Now I'm going to go with the second order. So I can write R is proportional to A to the power Y. To remove the proportionate sign, I'm adding the rate constant K. So I can write R equals K A to the power Y, which Y equals to 2. So that directly I can write the first expression R equals K A to the power 2. That is my first expression. Then you can get the units. K prime equals R divided by A to the power 2. See, A to the power 2 is small 2, dm to the power minus 6. So the K prime units for rate constant of second order reaction is cubic decimeter per mole per second. But still, this is the rate. Then I'm going back to the same way. Initial rate equals R equals A over time. Then again, concentration of initial A is constant. So initial concentration of A is constant. So that instead of this A, I'm writing K2. See, K2. So R equals A over time become R equals K2 over time. R and R cancelling off, I can make so that K prime A to the power 2 equals K2 over T. K prime A to the power 2 equals K2 over T. K prime A to the power 2 equals K2 over T. This time I'm subjecting A to the power 2. So that this K prime goes down here. These two together cancelling off to give the real K, which equals A squared equals K into 1 over T. Same way, I'm going to draw these three graphs. Notation last. Then from the first equation, R equals K A to the power 2. R equals K A to the power 2. I can draw this Y equals MX kind of graph. See, R equals K A to the power 2. If I get R is to Y axis and A to the power 2 is to X axis. So that's supposed to be a straight line going through the origin. Is that clear? Y equals mx kind of a graph. Y equals mx kind of a graph, but y is supposed to be r and x supposed to be a to the power 2. Then from this second one, this second expression, I can write again if I remove this k. If I remove k, I can write a2 is proportional to 1 over t. So a to the power 2 and time has inverse relationship. Again, I'm getting this hyperbolic curve. But if I just go with this one, y equals mx. See, y equals mx. That's again y, so that is a to the power 2. X equals to 1 over a. If I go 1 over t. 1 over t against a squared, again I is supposed to get y equals mx kind of a graph. Clear that? Then one more extra is here. See, this one is straight line because we have drawn between r and a to the power. So direct relationship is there. Y equals mx kind of relationship is there between r and a to the power 2. So when a to the power 2 increasing, see each time rate also is increasing. It simply means when we are changing a, rate is increasing linearly to a to the power 2. If we go with a, not a to the power 2, if we go with a, it's supposed to be increasing, but that's not linear. To be linear, this is supposed to be go with square value. Understood? So that this is exponential increasement. Exponentially mean this shape. Exponential increasement, but it is not a straight line. To be straight line, we have to go with a to the power 2. But here I'm just getting a. Is that clear? Understood? Okay. So now tell me, if I go with a to the power 3, what is this reaction with this equation? Third order. A to the power 3 equals k into 1 over t. Then this is exactly same a to the power 3. Here a to the power 3, a to the power 3, a to the power 3. This is again a to the power 3. This is, if this is a to the power 3 is again a exponential curve. Understood? So the next one you're going to do all by yourself as a homework. Okay, let's copy this one first then. Okay, copy from here. Unfinished? Oh, good. Okay, copy the rest. Copy up to here. Rate increases exponentially with concentration of A. Rate increases exponentially with concentration of A. Finish. Okay, see, again, I'm going to go to this first equation. My first equation is R equals Ka to the power 2. I'm going to go with log values of that. See, I'm going to convert that to log. So I can write, instead of R, I'm writing log R. Instead of K, I'm writing log K. Then you have, in between K and A, you have the multiplicity become plus. Then the power become the multiplicity, so that 2. Then A become log A. So I'm going to rearrange this equation. 2 log A, I'm going to get to here. And log K, I'm writing here. Just a rearrangement. Then I can arrange this one as log R is Y. So for the y-axis, I'm writing log R. So this is the log R. Then my x-axis is log A. See, the log A is my x-axis. Then you're going to get y equals mx plus c, kind of a graph. Then my c is log k. So log k is c. So that using log k, intercept, from the intercept, so that I can find the rate constant. And then gradient. My gradient m is 2. So knowing the gradient, I can calculate the order. 2 is the order here. Clear. Using this method again, you can calculate K and order. Okay, let's copy this. Also, just write also and then copy this. I tried to find this pencil so badly yesterday. That was not clear today. Huh? This pencil, I tried to find so badly yesterday, I couldn't find it, and I got a new one. Today it's on my desk. Yeah, what is the reason? Okay. Booby dosha. Booby dosha is ghost dosha. Maybe a ghost is here. Maybe there. You know, you have a very good brain. Karna, do you know that? Arham is the best example. There was a boy, Dilshan, he was in, I don't remember his year, I guess 2021. Sort of same, so playful, not working enough. The very first, like, their marks are very low. His marks are very lower. But you know, the teachers have instincts to see whether the student is like have the future or not. Then I said, I'm challenging you. If you do this and that, you can get to there. That you can do that. Then finally he became district fourth, I guess. District fourth. I just speak to. He was in 2020 batch. District 7. Dirishan Kulatilaka. District 7. He just spent his first early stage of advanced level like not trusting. Okay, so let's write this point. Using this graph, rate constant, using this graph, rate constant K, within bracket intercept. Did you write that? K within bracket intercept and order of the reaction within bracket gradient can be determined. Okay, now rate is proportional to a to the power 2. Okay, so that when rate concentration for second order reaction, when the concentration becomes twice, rate becomes increasing in 4 times. Clear that? So if the rate increasing 4 times, when you increase the concentration twice, when you double the concentration, if the rate increases 4 folds, then the order equals to 2. Yeah. If not changing, even if you are changing the reactant, reaction rate is not changing. Order 0. If you double the concentration, rate doubles. Yeah, first order. If you double the concentration, rate 4 times. Second order. Understood? Okay, let's write that. For second order reactions, comma, twice the concentration of reactants. For second order reactions, comma, twice the concentration of reactants, comma, R get increases by 4 times. R get increases by 4 times. Okay, so let's write the inverse of that. Therefore, next point. Therefore, when we double the reaction rate, therefore, when we double the reactant concentration, comma, if reaction rate increases by 4 times, comma, then the reaction is second order. Okay, so the topic, third order reaction. Let's write these homework, let's write these equations. Copy these equations. Okay, then use a pencil to write this. Use a pencil. This is your homework. Derive, pencil. You're going to delete that later, okay? Derive rate law for third order reaction, and draw graphs. See, this is the third order rate expression. Then you can write the units same way. Then again, I haven't shown that, you know, the Rate is proportional to A divided by T or K divided by T. From that, you can get this one. So then you are drawing first 3 diagrams to A to the power 3. A to the power 3. And then the last one just to A. So it has this exponential increasement. Copy the second one, analyze the second one, exactly the same way you are doing that. And then again you are going here, then go with log values, then again you are drawing the same diagram. Okay, whatever the space that you left for, you did for second one, just leave the same space. I would say one whole page for me, one whole page, is it? Starting from the writing this equation. Okay, then I want you guys to copy this table. This is again homework. You're going to fill this at home. Nidula, did you go through these paper class recordings? It's a must. But before that, you have to do the tunes as well. I know we don't have time. You guys are really, really around, but still, you have 10 more months. I'm pushing you. Just work like hell. Because they were not postponing these 24 exams mean they were given this date like, you know, how many months ago? Like more than 1 year ago, they were given this. Finish. Finish. Okay, next topic. Summary of graphs. Summary of graphs. See, first graph between rate and concentration of A. See, between rate of concentration of A. If it is concentration of A, if it is first order, that's a straight line. Zeroth order, that is a straight line parallel to this x-axis. But for second order, third order, fourth order, fifth order, go like this. And again, if you go with the rate and time, it is constant for zeroth order. So the first order, second order time is decreasing. What's the meaning of time is decreasing? To occur the reaction. Rate is increasing. Clear that? Less timing mean faster, higher rate. And then this is the log value. So again, zeroth order, first, second, third, y equals mx plus c kind of graph. Clear that? Copy these three, hurry up. I shouldn't give these, but I'm giving these to give you guys this intense practice. Hurry up. Need to learn anyhow. Try these three girls to get to the morning class. Sanjana and those three. Otherwise, time is not enough. Moving on. Okay, overall order mean the addition of all these orders. How many orders regardless if you add, let's say, a to the power x, b to the power y, c to the power z, x, y, z together is called the overall order. Let's write the topic. Overall order of the reaction. Overall order of the reaction. So they are giving a long calculation and then finally they ask what is the overall order. You can add these orders together. Let's write the point. This is the summation of all orders. This is the summation of all orders with respect to each reactant. With respect to each reactant. This is the summation of all orders with respect to each reactant. If, next point, if, copy this. R equals K, A to the power X, B to the power Y, C to the power Z. Then let's write overall order equals X plus Y plus Z. X plus Y plus Z. Manjula? Okay, let's do this question. Manjula මට කියන්න අමතකයි කියලා කිව්වේ 12ට කියුට් එක දෙනවනේ පටන් ගන්නෙදි 12 තව මාසයක් තියෙනවා. English Sinhala දෙකම. Okay, question Q4. Q4. Let's copy this equation. Is a single step reaction. Is a single step reaction. For given concentrations of A and B, for given concentrations of A and B, comma, the rate of the reaction is equal to R. The rate of the reaction is equal to R. When the concentration of A and B are doubled. When the concentration of A and B are doubled, comma, the rate of the reaction may be given by the rate of the reaction may be given by the rate of the reaction may be given by. Okay, get the answer. Two A plus B gives 2D. So 2D we can forget because the rate goes with rate expression, rate law always with reactants. They say it's a single step. Okay, if it is a single step, order equals stoichiometry. Since you guys are very new, I'm just saying that. Since it's single step, order equals stoichiometry. So they say rate equals to R when they double the reaction rate. When they double the reaction rate. Try. So they are double the reaction rate. So let's get that initial A concentration is A, B concentration is B. But later they double mean A become 2A, B become 2B. So you can write two different equations. So they're given R, Baba. Okay. You can keep it on the table that they're going to sweep this every day. What's the idea? What is the answer? Okay, first equation I'm writing, they were given as R equals K A to the power, because order equals the stoichiometric ratio, A to the power 2 into B to the power 1. Then the second one I'm going to get as, let's say R2 equals to what? A into 2A to the power 2 into 2B to the power 1. Then divide 1 by 1. Understood. Then get the connection between R and R2. In terms of R, what is R2? Midula, why? Shama, what is the answer? Yeah, well done. 8. See. Don't write, just listen. Okay, this is the initial condition. They say this is an elementary. So rate equals the stoichiometric ratio 2 and 1 here. Again, you have 1 here as well. Then this is the normal rate, R1, for the first condition. Then the second condition, they say A is doubles become 2A, B is double become 2B. So that now I'm going to divide 1 by 1 so that K to K is cancelling off. Then 2 to the power 2 become 4. Then A to the power 2. Then here, this is just 2B. This one I'm just writing as it is. Then I can cancel off A to the power 2B, then K and K, then 4 multiplied 2 is 8. Then R2 equals, R2 divide R1 equals 8. Then R2 equals 8R1. So the answer is, I have taken R1, they were given just R here. So the answer is 8R. Okay, let's try this point. Since it is an elementary reaction, comma, stoichiometric coefficients are equal to, stoichiometric coefficients are equal to order of the reaction. Order of the reaction. This is an exam question. See how easy they are. Stoichiometric coefficients are equal to order of the reaction. Okay, then copy this. So instead of stoichiometric coefficients, we are writing the order. Okay. Anyway, so after this, we are going to understand these 3 different experiments. We're going to do 3 different experiments to understand the reaction rate and to calculate the order. First one is between, remember the same way that I have explained this for this analytical chemistry, that there were 3 reactions. What are those 3 reactions? Fe2 plus KMnO4. Then what is the second one? Oxalic and KMnO4. Then the third one, Fe2 plus and potassium dichromate that we need external indicator, diphenyllamine, remember. The same way you have three reactions, say you have to memorize magnesium and H2SO for what are difficulties, what are the challenges, how do you overcome, then how do you measure the reaction rate, then sodium thiosulfate and HCl. What is the product of sodium thiosulfate HCl? Any thiosulfate, addition of any acid. What are the products? Reducing SO2, making sulfur. Then see, ionometric titration we did. So we are using those knowledge here again. So that, let's say that we want to find the concentration of one component, we have to keep the other component constant. Two components together, we cannot find the order. To get the order of one thingy, other thing is supposed to be constant. To understand that, we are doing this calculation. So we are doing this calculation and let's start that after the break. So the time is for, let's say 4:05. Do you want 15 minutes? Okay, you can finish your lunch with these two. Okay, get 15 minutes. Come here at 4:20. Okay. Then 1 more hour class. Okay, get the break. Come back at 4:20. Yes. I'm in my mind, do you have that attitude? I'm really struggling, like, I don't know how these tuition people are just doing all those like rubbish stuff in front of students, not doing enough. I feel a little like nervous now. How would I manage everything in this 10 more months? Okay, they would come to the experiment like this. Consider hypothetical reaction. Consider hypothetical reaction given below at a given temperature, at a given temperature. Okay, let's copy the equation. At a given temperature. Ronnie, do you see my way? No. So you see only this up to this level. Okay, that's right. The rate of the reaction is 5 into 10 to the power minus 4 moles per cubic decimeter per second, when concentrations of A and B are 1 into 10 to the power minus 5 moles per cubic decimeter, 1 into 10 to the power minus 5 moles per cubic decimeter, and 1 moles per cubic decimeter, respectively. If the rate doubles, as the concentration of A, you write like this, okay? As the concentration of A doubled. If the rate doubles as the concentration of A doubled, comma, calculate the rate constant of the reaction. Okay, some sort of reaction they are given. So these are the reactants. Let's say with respect to A, order is X. With respect to B, order is Y. So rate we are writing R equals, rate constant is always K. We have two different reactants, A and B. So the concentration of A and B, but we have to raise with the stoichiometric, orders of that. Let's say with respect to A, order is X. With respect to B, order is Y. And then they say another little data. If the rate doubles as the A concentration doubles. So with respect to A, what is the order? Rate doubles when A doubles. First order. Yeah, that's the first order. See, since rate doubles when A doubles with respect to A, so X equals to 1. See, this is the first order, X equals to 1. So that's the first order. Then another data is there. If you compare these two concentrations, 1 into 10 to the power minus 5 and 1. 1 is for A, 1 into 10 to the power 5 is for A, 1 is for B. So if you analyze these two concentrations, see 10 to the power minus 5, and this is just 1. So 1 is really, really high. So B's concentration changes very negligibly comparing to this concentration. Because the concentration difference is supposed to be really, really high. So really, really low, because initial concentration is really high. So that then we can say, if you compare A and B concentration, so this is a B concentration. See, the B concentration is really, really greater comparing to A, so that we can assume B's concentration is a constant, which I'm going to get as K prime. So that my rate expression I'm going to modify. I'm just writing R exactly the same way. R I can write as R. Then this B concentration is really high. So instead of B, I'm writing K prime. Instead of B, I'm writing K prime. And then A, I'm just writing as it is. Now with respect to A, X equals to 1. So X, I'm writing as 1. And then we already had this rate constant, which is K. This K and K prime, K1 together equals K prime. I'm writing R equals these two together K prime a to the power 1. So my rate expression is now R, K, A. They are asking K or the constant, rate constant, given that rate and A's concentration they have given as 1 into 10 to the power minus 4. And then the rate they were given as 5 into 10 to the power minus 4. 5 into 10 to the power minus 4. A's concentration equals, see, it's given here. A is 1 into 10 to the power minus 5. If you simplify those two, K prime equals 50, then moles per cubic decimeter cancelling off so that per second is remaining. Very similar. Seriously. Okay. So currently we have written the question, this question. Okay. So leave how many rules, Dhoni, for question? Just leave 6 up to here. Then start copying from this. Okay, I'll put it like this until Shamodi writes. Then I'm going to go, okay? You are writing the answer? Karna, you're writing the answer? Okay, then I'm going to copy this. Okay, Karna, see. Now, Nidula can't listen. Okay, so in the question, I'll give a question. In this question, concentration of B is really high. So that we consider B's concentration as constant. Knowing the B's concentration as a constant, we can calculate either R or either K or either X. Clear that? So that's how we are arranging, planning these experiments to find order. When you have two components, we make one constant, then we can find the order with respect to the other. Clear that? Okay, how much space is supposed to leave? Half a page, or maybe 3/4. Quarter. Yeah, more than half. More than half. Okay, let's write points. As in Q5, comma, when a concentration of one reactant is as in Q5, comma, when a concentration of one reactant is in large excess. One reactant is in large excess compared to the other reactant, compared to the other reactant, comma, it has been assumed that the concentration of that reactant, can be considered a constant, during the course of reaction. During the course of reaction, C-O-U-R-S-E. During the course of reaction. This postulate can be used to investigate the kinetics of reactions, involving more than one reactant, and the experiment can be designed as such. Okay, as I have explained, there are three different kinds of reactions: magnesium sulfuric, sodium thiosulfate HCl, ferric and Ai. In magnesium and sulfuric, okay, what would you know about this? Okay, there are two different reactants. With respect to what reactant, we can measure the order here. Since we are going with concentrations, we cannot measure solid magnesium concentration. So we're going to measure the concentration only with respect to sulfuric. So we are not worrying about the concentration making constant of magnesium whatsoever. And then the second one, we are going with sodium thiosulfate HCl. Both are aqueous solutions. So we can get the order with respect to both separately, keeping thiosulfate constant to get the order of HCl, keeping the HCl concentration high or constant, getting the thiosulfate. This one is also the same. Clear? And again, we needed some sort of observation here. What's supposed to be the observation here? So this is a reaction. What is the observation? Yeah, gas. How much gas is releasing? Okay, so let's try the topic then. Let's go one by one topic. Experimental determination of order of a reaction. Experimental determination of order of a reaction. Copy these three subtopics. 1, 2, 3. Okay, so this one, what would you do? Okay, we decide that we're going to find the order with respect to H2SO4, so that we are reacting it with magnesium, so that this is the reaction. So we have a clear observation to get the volume of H2. This is not we are determining whether the reaction is occur or not. To consider whether the reaction is occur or not, what is the observation? Bubbling of H2 gas that you would see. H2 gas is bubbling once you mix these two together. But this time that's not enough. We need to get concentration difference divided by time to get the rate. So we need to get this volume of H2 producing. What we are doing is we are getting a little test tube. Get the little test tube. Wash, dry, then everything done. Then we are adding exactly 10 cubic centimeter of water to this. Then we make, let's say this is the water level and this is the water level. Then we mark this with a rubber band. Then we are putting a rubber band around this, just exactly on the mark. Then we remove the water. Then we have exactly mark which we can fill whatever 10 milliliters. Then what we are doing is we are fixing this. Now we have the mark. Let's say we have the mark here. Now we are fixing this little cork here. And to that cork, we are fixing this glass tube. At the same time, we are fixing this, not onto this, separately. We have a separately cork. To that, we are fixing this glass tube. In there, we are trapping this little piece of magnesium. Clear that? Okay. Yeah, is that the way I have to draw that? Opposite upside down. Anyway, so then what we are doing is we are fixing this on here. Still the magnesium is not touching this. Okay, sorry. Before that, we are filling this one with now sulfuric acid. We are filling this with sulfuric acid. Then we are fixing this on here. When we are making this upside down, right at the moment we are mixing these two together. So this is starting to bubble. Right at that moment, we are starting the stopwatch. And we measure the time until this water level goes down up to this rubber band. There. Then we are measuring the time taken to fill 10 cubic centimeter of H2 gas. Understood? So this H2 gas 10 milliliter each time is constant, but is varying. With different concentration of H2SO4, what do we measure? We are measuring the time. So the time is varying. When the time is less, it is high. So when the concentration is supposed to be greater, is that clear? Time is, let's say it's going a long time, then the reaction is slow. Then the concentrations are low. Clear that? Okay. So then what we are doing is we are making this kind of a table. So let's say we are initially using just a mother solution. Let's say we have this big H2SO4 solution. From that, we are taking 10 cubic centimeter, 20, 30, 40. So when we are changing volumes, what do we change? Number of moles inside is changing. So this has, see the 1 H2SO4 10 cubic centimeter, 1 H2SO4 40 cubic centimeter. So the number of moles are greater. Okay, that. So as well, the time is also changing to collect exactly 10 milliliter of H2SO4 gas. Understood? Okay, then how do we go with the calculation? See, rate is proportional to H2SO4 concentration to the power n. Because magnesium is anyway constant solid, so the only one single reactant is H2SO4. Let's say the unknown order equals to n. But we are not measuring concentration here, but here we have measured this volume. And since we are using the total volume constant, because we are using the same mother solution, we can say concentration is proportional to volume taken out. So that instead of concentration, we are going with volume. To remove the proportionate sign, I'm adding proportionate constant. So my first equation, so that is R equals K VH2SO4 to the power n. Then I'm going to go with the second equation, C. Rate we can get again from H2 volume divided by time. Clear? But what do you know about the H2O volume? That is constant, always 10 cubic centimeter. That's a constant. So then write VH2 is constant K2. So instead of this VH2 form, I can write K2. So this is my second expression. First expression, second expression. R side is same, so that K1 VH2 SO4 to the power n supposed to be equal to K2 divided by 2. K1 VH2 SO4 to the power n equals K2 divided by 2. From that, if you subject this one, you can get K into 1 over T. So that using first order, second, third, whatever these drawing graphs. So what sort of methods we can find the order then? Is that clear? To find the order, we have a couple of 3 methods actually. Later we're gonna do calculations to understand all these methods separately. For now, we are just writing the method. So what do? We need to measure the rate of this reaction. So what we are doing is we get different H2SO4. Then if you write the rate expression, we can write R equals K H2SO4 concentration to the power unknown N. But we are not measuring concentration, we are measuring volume. If you want, you can measure the concentration, but why we worry? We can get the volume easily. Why we worry about measure the concentration? So we are measuring the volume. So that I can write R equals K V H2SO4 to the power N. That is the first equation. Then the second equation, R equals H2 divided by time. But H2 concentration is again constant. So that I'm writing, yeah, K over T. From that, I'm deriving the same way that you derived first, second, third, fourth order. Same way you derive the equation here. Understood? Is that easy? So let's write. So the very first topic we have written experimental determination of order of a reactant. Under that, the very first one, let's write topic number 1. Determination of effect of concentration. Determination of effect of concentration of H2SO4 and magnesium on reaction rate. Let's copy this equation. Okay, points. To determine the reaction rate, time required to collect a constant volume of gas, can be considered. Next point. Place 10 milliliter of water. Place 10 milliliter of water in a boiling tube. And mark the level with a rubber band. Next point. To the same boiling tube, add dill H2SO4 acid, according to following table, and fill it with water. Next point. Place a clean magnesium ribbon. As in the diagram, to the bung, B-U-N-G, to the bung, within bracket, cork. I'm giving this word because in case if it comes to the exam, B-U-N-G, bung, mean the cork, within bracket, cork. Next point. B-U-N, mean cork. Next point. Start the stopwatch while Turning the boiling tube upside down. Start the stopwatch while turning the boiling tube upside down. Turning the boiling tube upside down. Next point. Find the time required. Find the time required to collect. Find the time required to collect constant amount of gas. Find the time required to collect constant amount of gas. Okay, let's copy this. Moving on. Okay. Topic. We are still at the same experiment, okay? Topic. To determine the order of reaction. To determine the order of reaction. To determine the order of reaction with respect to H2SO4 concentration. With respect to H2SO4 concentration. Let's copy the table with respect to H2SO4 concentration. You could tell me. They said this camera is that sensitive, so I'm trying to catch those letters on the table, that cards. I was trying to catch those. Just tell me if you guys done. Huh? I have enough pictures of you. Okay, let me explain this calculation again. So the concentration is proportional, but we are not measuring the concentration, we are measuring the volume. So I am coming from concentration to volume. And then to remove the proportionate sign, adding the proportionate constant. At the same time, I can write the second expression, R equals to formed H2 divided by time. But formed H2 is constant, so that instead of this VH2, I can write the K2. So I have two expressions, this and this. If R are equal, I can write the other side equals as well, so I can get here. So from that, how do we calculate the concentration? So the order, that's we're going to do later. So let's copy this part. So let's write this little subtopic, calculation. Calculation, and then copy this. Something comes, but I cannot read the test. That blue one. Inside the blue one. It's amazing, but still, yeah. That little thing, it's clear, but I can't read it. See these flowers on that wrappers and everything, it's coming like, see the flowers. So it's sensitive, I guess. That's behind that. Yeah, cool, isn't it? That sounds frustrating that to maintain this white color casing is little real tiring now. I have to wash my hands always to keep the phone. No, the very first days you like keep all these like keeping on these velvet clothes and everything, but later, oh, my other phone having lots of discriminations. Can I move up here? So I'm trying my max to finish this unit within 4 weeks. So it simply means we're going to do another 3 weeks. This then we are moving to equilibrium, which I'm so excited to start. So Dhoni, are you living in like closer to this house or somewhere? Like, do you know where he lives? Puttapiti? No idea. Where do you live? Ah, it's before the town. Okay. These are just, I'm just writing this, a couple of factors. I just want you guys to consider one thing here. When you are drawing this glass tube, just check your diagram whether you have drawn this one above the cork level or just the normal cork level. You cannot draw like this. This is wrong. You have to draw it this way. Exactly this there. Is that clear? So the meaning is, if you make it little above, then see this part is a part that you are gathering this formed magnesium chloride. It decreases the reaction rate. So when you are fixing it, you have to fix it exactly this way. Then you have to wash this and so on. All are these little these experimental errors. Let's write those little. You can understand this easily. Let's try. Anyway, this stuff I read. Special factors, a little subtopic. Special factors to consider during the experiment. Special factors to consider during the experiment. Special factors to consider during the experiment. Okay, number one, surface area affects the reaction rate. Surface area affects the reaction rate. Therefore, same surface area of magnesium ribbon, same surface area of magnesium ribbon, same surface area of magnesium ribbon should maintain when fixing. Should maintain when fixing. Number two. If the glass tube fixed above cork level, if the glass tube fixed above cork level, comma, formed magnesium sulfate will be retained. Formed magnesium sulfate will be retained around the magnesium ribbon. Around the magnesium ribbon. Around the magnesium ribbon. This will reduce reaction rate. This will reduce reaction rate. Number three. To give identical reaction condition, comma, boiling tube with same mark should be used. Boiling tube with same mark should be used. Boiling tube with same mark should be used. Should be used. Number four. Cleaning of the boiling tube is necessary. Cleaning of the boiling tube is necessary. Cleaning of the boiling tube is necessary in each time. In each time. In each time. Number five. Starting from the lowest concentration. Starting from the lowest concentration and go through the highest. Go through the highest. Will minimize concentration errors. Will minimize concentration errors. Because in case the test tube were not washing enough, concentration can be changed. Last one. Should use an evenly cleaned magnesium ribbon. Should use an evenly cleaned magnesium ribbon. Just read once or twice, then you can just neglect that part, okay? Not that important. I'm just giving in case never come to the exam. Okay. Drama. Okay, topic number 2. Let's try the topic number 2. Determination of effect of concentration on the reaction between, first one is the magnesium H2S. So for the second one, sodium thiosulfate HCl. Number 2, determination of effect of concentration on the reaction between sodium thiosulfate and HCl. Sodium thiosulfate and HCl. Na2H2O3 and HCl. Na2H2O3 and HCl. Okay, if you remember, this is the reaction of inorganic chemistry. Whenever you are adding any acid to thiosulfate, it is releasing SO2 gas plus sulfur. Now tell me what is the observation here? Measuring observation. Baba, can do that later. Come on. What is it? Oh. Just say now. Just right now. On the way. Just sometimes act like an adult. Yeah. Okay, what is the observation? You have SO2 gas and you have sulfur. We are not getting SO2 gas. Why, Shamali? Because we cannot measure. This is really water soluble, not like H2. So we are going with this sulfur. Clear that? Okay, copy the equation. We did this equation for unit 6. All those equations now we are doing for equilibrium also we have done already for unit 6. Points. Come on, Karana, don't write. I'm waiting until you're done writing. That's right. When there are several reactants, comma, to determine order with respect to one reactant, comma, others should be kept constant. Others should be kept constant. Topic. Determination of order with respect to HCl. Others should be kept constant. Topic. Determination of order with respect to HCl. Now tell me, if we determine the order with respect to HCl, what concentration we keep constant? Thiosulfate Na2H2O3. Sorry. Keeping the Na2H2O3 constant, okay? What do we do here? Okay, so we have HCl and thiosulfate. We take, have you guys done this at school? Did, yeah. We take what? We take A4 paper. On that, we are drawing a pale color, black color cross. Why pale color? Because we want to deposit sulfur soon. Otherwise, it takes a lot of time to get the time. Then we place our beaker on that. Then we are observing on the top. The beaker consists sodium thiosulfate and HCl. So the beaker has sodium thiosulfate and water filled here, but still is transparent and colorless. So we would see this cross nicely. Onto that, we are adding secondly HCl. Somebody is watching here. Right at the moment you are adding HCl, we are starting the stopwatch. Once you add HCl, it is making sulfur. That sulfur is depositing on this. And then little by little, it's fading the cross. Finally, it's disappearing the cross, covering with sulfur. Then we stop the stopwatch. So we are measuring the time taken to disappear the cross. That equals to make the exact amount of sulfur. Because exact amount of sulfur needs to disappear this cross each time. So we are measuring a constant amount of sulfur this time. So what is changing? We are changing, let's say, one time thiosulfate concentration, second time HCl concentration, so that we are measuring the time. If the reaction rate is high, faster, so time taken is supposed to be low. If this reaction is very slow, it takes more time to measure. Clear that? Okay. That is this simple reaction. That is this simple experiment. Okay. So let's write points. You have written the topic. Determination of order with respect to HCl. Let's write points. The concentration of HCl must be varied. The concentration of HCl must be varied by keeping concentration of sodium thiosulfate constant. Concentration of sodium thiosulfate constant. Next point, to get different concentrations, comma, different volumes are used from same solution and total volume of the mixture is kept constant. Total volume of the mixture is kept constant. Total volume of the mixture is kept constant. Why we are keeping the total volume constant? Because then only we can see through and we can see that this whatever the solution height doesn't affect onto that disappear in the crossing. That whatever the vision is not disturbing. Okay, so if you are going with respect to HCl, so we are keeping this sodium thiosulfate constant. So the same volume has same number of moles. Here, same other solution we are using. So depending on the volume, number of moles is different. Anyway, to give this uniform reaction conditions, we are making the total volume constant by adding water. This time, see if you can calculate any of these. Total is 15. So the V total here we are taking 15. Clear? Okay, copy this table. These are extremely easier. If you concentrate enough well, these are very easy. V total equals 15 cubic centimeters. V total equals 15 cubic centimeters. You don't want it. Okay. Coils. 0.1 m sodium thiosulfate and 0.1 m sodium thiosulfate and Kalna, you done writing. 0.1 m sodium thiosulfate and H2O are mixed in a beaker, comma, according to above table. According to above table. Next point. A cross was marked on a paper. A cross was marked on a paper using black ink. Next point. The beaker is kept on the cross. The beaker is kept on the cross. The beaker is kept on the cross. Okay, this is how you are doing. So you are doing this way. Firstly, you are adding sodium thiosulfate to that. While you are turning on the stopwatch, you are adding HCl. Then you are checking here until the cross disappearing. I want you to draw both these diagrams. 1 and 2 mean firstly you are adding this, then you are adding HCl. Okay, points. When adding the HCl solution, when adding the HCl solution, start the stopwatch, and find out time required to disappear the cross mark. Time required to disappear the cross mark. Okay, so the same experiment we are doing to get the order with respect to thiosulfate. Same experiment. Let's write the topic. Subtopic. We are still under thiosulfate and HCl, okay? Subtopic. Determination of order with respect to thiosulfate. Determination of order with respect to thiosulfate. Are you guys okay with the speed? We are going really speedily today. So that's why I'm having the faith that we can finish this within 3 more weeks. Points. Same procedure is followed, but the volume of sodium thiosulfate, is varied while keeping the HCl volume constant. Looking at the table, you can say that this is constant mean we cannot get the order with respect to that. See, this is changing. So here this time we are getting the order with respect to sodium thiosulfate. Copy this. We total 30 cubic centimeters. We total 30 cubic centimeters. All right, let's write. We are done with that. Just again, these experimental errors whatsoever, let's just write. You can understand this topic. Special points to consider in the experiment. Special points to consider in the experiment. Special points to consider in the experiment. Let's go one by one. Use of a small beaker. Number 1. Use of a small beaker. Use of a small beaker. Number 2. Drawing a pale color cross. Drawing a pale color cross. Why is that? Small beaker, pale color cross. Yeah, to save timing. To save timing. Otherwise, it takes a lot of time if you use a large beaker. Cover the cross, we need a lot of sulfur. Number 3, use of the same observer. Number 4, use of same cross. Use of same cross. Why is that? Again, different observers see the cross disappearing in different ways. Okay, so the visual effects. Number 5, cleaning and drying the beaker each time. Cleaning and drying the beaker each time. Cleaning and drying the beaker each time. Number 6, choosing of an accurate timing device. Choosing of an accurate timing device. So the stopwatch is supposed to be work nicely. Choosing of an accurate timing device. Number 7, since rate depends on temperature, comma, choosing of a good thermostat. Choosing of a good thermostat. Thermostat means to control the temperature. Choosing of a good thermostat. Okay. Now we are trying to calculate, to understand how do we calculate this. I know we don't have enough time, but I can give you guys the big picture. So let's try the top question. Next day we're going to do the practice, okay? Let's try the topic question. Q6. Following data were obtained. Following data were obtained in the experiment. Following data were obtained in the experiment. Which is used to determine order of sodium thiosulfate and HCl. Sodium thiosulfate and HCl. Find out Roman number 1, order with respect to Na2H2O3. Order with respect to Na2H2O3. Number 2, order with respect to HCl. Order with respect to HCl. Order with respect to HCl. Number 3, total order of the reaction. Total order of the reaction. Total order of the reaction. Number 4, time within bracket T1 in first table. Okay, they are not giving such for final exam. They are giving one single table, keeping sodium thiosulfate and HCl together. But since this is your first time, I'm giving sodium sulfate experiment separately and HCl experiment separately. If here we are going with sodium thiosulfate, what is it with HCl? HCl is supposed to be constant. And here we are going with HCl, so sodium thiosulfate is supposed to be constant. Okay. Any idea looking at this one? Who can tell me what is the order? First, Tony, this is 1 over T. Understood? So 20 mean slower, 10 mean faster, 20 faster, 10 slower. So why increasing? Just twofold. What is the order here? 0. Why? Even when the concentration is changing, Karana, time is not changing. Understood? So that is the simplest way. Even for that, there will be marks for final exam. Then you have to write words and explain that. Since the temperature is constant with respect to HCl, even then when you are changing the concentration, so then the with respect to HCl order equals to 1. So you have to write like that. When the temperature, when the concentration doubles, then the rate, you have to write like rate is equals 1 over T. Then you can do calculation, both are like, this is decreasing. So rate increases when concentration doubles. So with respect to sodium thiosulfate, order equals to 1. Okay. So that is the simplest way, but we're not going to go through like that. We can go through this graphical method. In the graphical method, whatever the way, see. So we have this both together. Let's say I'm going to go only with thiosulfate so that I can make HCl constant. So I can forget that. So I can come in here. But here again, we are measuring the same other solution's volume. So instead of concentration, I'm going with volume. So I can write R is proportional to volume. Then again, the same time. Can we say the amount of sulfur is constant? Each time, same sulfur, same cross covering. So the second rate equals amount of sulfur divided by timing, but the amount of sulfur is constant. So I can write K here. Then again, I have two R's. R equals Vs2O3 to the power N. R equals K divided by time. So using those two, I can come up here. Or proportionate sign, I'm going to remove that, equals K into 1 over T. So either using this 1 over T or either using T, whatever the method, I can draw these diagrams depending on C, 0th order, first order Vs2O3, then second order Vs2O3 to power 2. Clear? They never ask you this question. Nedula, come on. Are you going to go back to school now? Really? What time are you going to go home? Really? See how inspired they are for education? Seriously, guys, if you have this inspiration for education, you can touch the sky. Can touch the sky. But you guys are not doing that. Okay, this method is just not effective. We are just writing. But the second method. Okay, so Vs2O2 through to the power n, that proportional to 1 over T. So remove the proportionate sign, I'm adding K. Then I can end up rearranging, subjecting this T here, subjecting K here, I can end up this equation. What is the meaning of this? Vs2 to the power something multiply T is supposed to be constant. If it is 0th order, if this is 0, K equals to T. That is what happened for with respect to HCl. So the T is constant. So that's why it's 0 order. Or otherwise, we can go with calculating thiosulfate volume with time. Okay, thiosulfate volume with time. So I'm going to go here. I have my data. 20 into 10, 15 into 13, 10 into 20, 5 into 40. I'm going to calculate and see whether they are giving the constant value. Yeah, 20 into 10, 15 into 13, 10 into 20, 5 into 40. Almost same. So it simply means this is supposed to be true. Clear? This is supposed to be true. If this is not working this way, then what can we do is we're going to go with the square value of this. Then we're going to again calculate this value. Let's say now that is equal, then this is supposed to be 2. But here when this equals to 1, you are getting these values. So that with respect to thiosulfate, we can say order equals to 1. Clear that? Okay, graphical method, then value added method. Then third method is the simultaneous equation method. I want you guys to tell me which method is easier. Okay, so the simultaneous equation method means we are getting 2 different conditions. I'm going to go with this equation. Then I'm going to add 2 different values for these out of these. So I'm going to go with the second and fourth data. This is my second data. And this is my fourth data. 2010, then 10 and 20. 2010 and then 10 and 20. See. First data is when volume is 20, time is 10. Second data when volume is 10, time is 20. Okay, so N is just maintaining, K is just maintaining. If we divide 1 by 1, these two cancelling off, this become common, so that this divide this equals to 10 to the power N. Here again this equals to 2. Okay, so the base is equal. Then index supposed to be what? This is 2 to the power 1. Clear that? So that N equals to 1. Clear that? Okay, so this one again we can do exactly the same way. Then we're going to get the same 0th order answer. So the next day, it's 5:30. So the next day we're going to do all this. Refresh this little knowledge. If you, I prefer if you go through this recording and read this last part before you get to the class next day. And I can convince you very easily the next part for you guys. Okay, so I'm not going to do, do you guys need a refreshment? I know you definitely would say no. Shama, do you want a refreshment? Yes, I guess. Just for a second, Baba. I'm going to start it from this rate law. Rate law is going with the concentration is rate is proportional to concentrations, some sort of a power. So then we talked about this order. Then for 0th order, then power supposed to be 0. Power supposed to be 0. Then we can derive these 2 equations. Out of these 2 equations, we come up that when the concentration of that reactant is changing, time taken for the reaction is not changing. Then we derive these 3 equations. Then for first order, then power equals to 1 or the order equals to 1. So this is our first equation and this is the second equation. Add these 2 equations together so that we are coming to this final equation. From that we can derive these 3. I guess you want to hear this recording again. Then you can get a better, like very clear, crystal clear idea because we did a lot today. Then third and fourth exactly go through the same way. Then the last little part we did was this experimental part. To go through the experimental, I did this question number 5. When we are having a couple of these liquid reactants, make all these reactants constant, leaving one single reactant vary. So that we are using the same method here. Since the first one has the magnesium and H2SO, for anyway the magnesium is constant. When you are moving to the HCl and H2 thiosulfate, the HCl and thiosulfate both are aqueous, so that we're going to make thiosulfate constant to find HCl and HCl constant to find thiosulfate. Once you've done this experiment, there are 3 different methods: graphical methods, value-added method, and the third one is the simultaneous equation method that we didn't write any note. I've just explained to give you guys a push for the next day. Okay, so let's do that part next day. Any question, anybody? Okay, bye, take care then. It's at 9. So the next week, normal time, 2:22:65.